Good afternoon, class. We are looking at chapter 2, limits and derivatives. Exam 1 will cover the chapter from 2.1 to 2.8. We are going to look at the first part, covering from 2.1 to 2.3, 2.1, the tangent and velocity problems, 2.2, the limit of a function, and 2.3, calculating limits using the limit laws. So here's the synopsis of the chapter, the tangent and velocity problems, the limit of a function, calculating limits using the limit laws, the precise definition, continuity, limits at infinity, horizontal asymptote, derivatives, and rates of change to derivatives as a function. So let us get started here. 2.2, limits of a function, finding limits by numerical and graphical methods. Definition: limit of f of x as x approaches a equals L. The way we read this, limit of f of x as x approaches a equals L. The limit of f of x as x approaches a equals L. Let's look at all these graphs. We are approaching a in all cases. So we are going this way, from the left side of A, from the right side of A, along the x-axis. So the x coordinate is getting closer and closer to A. That's the meaning of this. We will never get there. We are getting closer and closer. So along the y-axis, from the bottom, from the top, we are getting closer and closer to L. Along the curve, we are getting closer and closer to this point. So if you look at every case, as we get closer and closer to A, the y gets closer and closer to L, and we are approaching this point. So they all give us the same limit. So the limit of f of x as x approaches A is equal to L in all cases. What about the differences among those? F of A, the functional value is precisely L for part A as well. However, here, f of A has a different value, B. In this case, f of A is not even defined because remember, both of them are wholes. This one, f of A is defined. This one, f of A is not, is missing. So part A, f of A equals L. Part B, f of A equals B, which is not equal to L. And part C, f of A is not defined. But in each case, regardless of what happens at A, the limit of f of x as x approaches A equals L. And that's the concept we should be very comfortable with. Limit means getting closer and closer, but never reaching there. Horizontal asymptote, HA for short, of the curve y equals f of x is y equals L. And it has the following definition. If the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches positive infinity equals L. Now, the limit of f of x when x approaches A, or this is called A from the left. It's not negative A from the left or A from the right. If any of them end up being positive or negative infinity, then x equals A is the VA, vertical asymptote. That's the definition, vertical asymptote. One-sided limits. A function has the limit at A if the limit of f of x as x approaches A from the left equals L, and the limit of f of x as x approaches A from the right equals L. Therefore, the limit of f of x as x approaches A is L. In other words, the limit on the left and right must be identical. And definition of a continuity says limit of f of x as x approaches a and f of a must be identical. As you can see, in this case, we have a continuous function because the limit of f of x as x approaches is L. Also, f of a is L, not in these two cases. So that's the synopsis of the concept of the limits. Now, let's find limits, finding limits by numerical, graphical method. And we also look at analytic methods. So let's start guessing what is the value for this limit. As you can see, if you set the denominator equal to 0, x is 1 or negative 1. And so as x approaches 1, this is not defined. So how does the numerical method works? We start getting closer and closer to 1 from the left side of 1 and from the right side of 1. In other words, here's number 1. The left side, numbers very close to 1, but less than 1, like 0.5, 6, 7, 8, 9, 9, 9, 0.9999, and so forth. So with the numerical method, the tables below give values of f of x correct to 6 decimal places for values of x that approach 1 but are not equal to 1. And that's the key, because when it's equal to 1 becomes the functional value. For x less than 1, for example, 0.5, 0.9, 0.99, and so forth. Please understand, this is way too far. Even 0.9 is way too far, okay? And we plug the numbers into this function, and we get those answers. Now, from the right side of 1, like 1.5, 1.4, 1.3, 1.2, and we get closer, 1.1, 1.01, and so forth. We get closer and closer, okay? And when we do that, so again, please understand that this is way too far. Even 1.1 is too far. So we're getting closer and closer, and these are the values. We notice when we get closer and closer to 1, the last one, which is the closest number to 1, this number and this number are closest. This is the value from the left. This is the value from the right. And if need be, you can even get closer by adding 9s here and adding zeros before 1 here. And I hope you recognize from the table, the limit must be 0.5. If we were to graph this from the left and right of 1, here's the graph. We are moving towards this point. Please understand there is a hole here. It doesn't mean the limit doesn't exist. The limit is equal to 0.5 as x approaches 1. The functional value at x equals 1 is not defined. Okay. So how do you do it analytically? Algebraically, you do factoring. You notice that the denominator can be factored into x minus 1 times x plus 1, reminding you that a squared minus b squared is a minus b times a plus b. So we can write this as x minus 1 over x plus 1. These two cancel each other and we get 1 in the numerator. And as you can see, if I plug in 1 here, I get 1/2. And that's exactly what we have here and here and here. So numerically, we showed the answer is 0.5. Graphically, we showed the answer is 0.5. Algebraically, we proved the same. Calculating limits using the limit laws. Let f of x and g of x be defined for all x over some open interval containing a. Assume L and M are real numbers such that limit of f of x as x approaches a is L, limit of g of x as x approaches a is M. And let C be a constant, just some number. Then each of the following statements holds. Some law of limits, limit of f of x plus g of x as x approaches a is limit of f of x as x approaches a plus limit of g of x as x approaches a, that means L plus M. In other words, the limit of the sum is the sum of the limits. This is the same thing, but difference law of limits. Limit of f of x minus g of x is limit of f of x as x approaches a minus limit of g of x as x approaches a. So that's the difference. Constant multiple, if we are multiplying a function by c and we take in a limit, we can take the constant out. This is L, so c times L. Product law for limits. The limit of a product is the product of the limits, L times M. Those are very straightforward. There's really not much to memorize. It makes perfect sense. A quotient law, the limit of a quotient is the quotient of the limits, and as always, denominator can't be zero. We can add to it like the power law, the limit of f of x to the power of n as x approaches a. You can take the limit of f of x as x approaches a and then raise it to the power of n, or L to the power of n. When you take a root, the nth root of f of x, and you take a limit, it's taking the limit first and then taking the nth root. That in that case, for all L, if n is odd, if the index is odd, there is no restriction. Okay. If n is even, then L must be non-negative. From now on, we're going to do direct substitution. So what is the direct substitution property? A continuous function at a has the following limit values. The limit of f of x as x approaches a equals f of x. Functions with the direct substitution property are called continuous at a. The squeeze theorem. If g of x is between f of x and h of x, in other words, f of x is less than or equal to g of x, less than or equal to h of x, when x is near a, except possibly at a. So what happens at a is not important. That's the concept of a limit. What's important to us is near a. If the limit of the left function, limit of f of x as x approaches a, is equal to the limit of the right function, limit of h of x as x approaches a, and both of them give us L, the one in the middle that is squeezed in between, limit of g of x as x approaches a, is also L. So very straightforward. All right, let's look at a very simple example where the graph is given and we are supposed to find the limit of f of x as x approaches 2. So to do that, we are going to approach it from the left and right. Again, the limit of f of x as x approaches a from the left equals L. The limit of f of x as x approaches a from the right is also L. Then the limit exists as x approaches a, which is L. That is important to understand. Otherwise, it's not. All right, let's look at the first case. As x approaches 2 from the left, means we are coming at 2 this way along the x-axis. So as far as the curve is concerned, we are coming this way, moving towards this point, which has the y coordinate number 3. Now limit of f of x as x approaches 2 from the right. So from the right side of 2, coming this way, we are in this branch, moving towards this point, and this point has an answer 1. So are they identical? No. The limit of f of x as x approaches to DNE does not exist. So that brings us to this question. So what is f of 2? Wherever you have a solid point, solid dot, for x equals 2, you see a solid point here, so the answer is 3. Now, the limit of f of x as x approaches 4, when we move towards 4 along the x-axis from the left side, it is moving us towards this point, which has the answer 4. As we approach it from the right side of 4, we are moving this way. And again, we are going towards the same point. So both sides are, remember, we never get to 4. We are just interested in the limit. So it moves us towards this point, which has a y coordinate 4. So the limit of f of x as x approaches 4 does exist, and it's equal to 4. However, what is f of 4? You look at the 4 along the x-axis. Can you find a solid point? The answer is no. Therefore, it's not given to us. Therefore, it's undefined. Undefined. Okay. One thing I want to make a point of, because these two are equal, sometimes they say the concept of a continuity, the function is discontinuous at 2 as well as 4. But at 2, it's continuous from the left. We will discuss that further later. All right. Again, we want to pay attention to the graph. And I'm reminding you of these definitions for VA, vertical asymptotes. So we want the limit of R of x as x approaches to. So you look at number 2 and you see that as we get closer and closer to 2 from the left and right, both, it seems to me that it's going down both sides to negative infinity. The limit of R of x as x approaches 5, left side and right side of 5. From the left and from the right, both of them seem to tend infinity. The limit of R of x as x approaches negative 3 from the left. Please understand the concept of left of negative 3 versus right of negative 3. So from the left of negative 3, from the left of negative 3, it's going down to negative infinity. However, from the right, from the right, it's going to positive infinity. And now we want an equation for the vertical asymptotes. The definition says x equals a is a vertical asymptote if the limit of f of x as x approaches either a or a from the left or a from the right is infinity or negative infinity. So look at those. So x equals 2, x equals 5. Both of them, as long as one of them is true, gives you x equals negative 3. Those are the vertical asymptotes by definition. To find the limit, just plug in and observe. So what happens? If you plug in and it gives you a number, you're done. That's the answer. If you plug in and it gives you 0 over some number, the answer is 0 and you're done. If it gives you some number over 0, remember previously we would say undefined, but it's either infinity or negative infinity. We further investigate to see which one is the case. However, in calculus, in most cases, we end up with indeterminate forms. 0 over 0, infinity over infinity, infinity minus infinity, which means you have to use your algebraic techniques to figure out the answer. Indeterminate forms, in short, means more work. So you have to work on it. Okay? So let's get started. I hope you recognize if you plug in 0 here, you get 0 over 0 because this is square root of 4, which is 2 minus 2 over 0 over 0. And 0 over 0 is indeterminate, more work. And therefore, you have to use some sort of a technique. The algebraic technique involving square roots is to multiply by the conjugate. The conjugate of a minus b is a plus b, and the answer is a squared minus b squared. Think of this as a minus b. So you just put a plus sign in between, becomes a conjugate. You multiply and divide by it. The reason you can't just multiply by it, because this is equal to 1 and it's acceptable. So what happens is the result will be square root of x plus 4 quantity squared minus 2 squared for the numerator. For the denominator, you don't do anything. You keep it as a product. So the reason you keep it as a product, because x is approaching 0 and the 0 in the denominator is a problem. You're hoping it drops. 4 and minus 4 cancel each other. X and x cancel each other. And if you plug in 0, you get square root of 4, which is 2 and 2 4. So the answer is 1/4 as the final answer. Let's take the limit of x plus 2 over x plus 3 as x approaches negative 3 from the right and negative 3 from the left. Please understand, every number that is positive, both sides is positive. For example, if I make up a number 5, both sides of 5 are positive. For example, the left side is like 4.9 and the right side is like 5.1. If I have minus 5, both sides are negative. Left side is like minus 5.1 and the right side is minus 4.9, which is larger than that. The only number that the left side is negative and the right side is positive and they have different signs is 0. Now, if you plug in negative 3, if you plug in negative 3, the first one becomes negative 1 over 0, the second one becomes negative 1 over 0. But we are not dealing with negative 3. The top one is negative 3 from the right. So you actually pick up a number from the right. I highly recommend you pick an example. You can even pick negative 2, but negative 2.9, we want to add 3 to it, and that gives us 0.1, meaning this is positive, everybody. So negative, see, a number over 0 is either infinity or negative infinity. Negative over positive is negative infinity. Pay attention to the way I find the answer. This one is negative 1 over 0 from the left. Here's the reason, because this negative 3 from the left is like negative 3.1 plus 3 is negative 0.1, and therefore the sign is 0 from the left. So what is the difference? The difference, both of them are infinity. This is negative infinity because negative over positive is negative infinity, but negative over negative is positive infinity. That's how you figure out the sign. You need to practice this. It's very simple.
So, Professor, you can plug in the negative. So for C, for example, where it shows x is approaching -3 from the left, you can plug in -3 on the top for x, or on.
Yeah. Here's the thing. When you look at the top, if I go from negative 3 from the left or right, makes no difference. The answer is almost -1.
Mm-hmm.
And almost -1 from the left or right makes no difference. It is -1. The only number that makes a difference is 0, because 0 from the left is negative,
Mm-hmm.
0 from the right is positive. That's why for the numerator, we don't worry about that. If we want to be more precise, -3 from the right, so it's -2.9 with +2. Just to give you an idea, we actually get, instead of -1, we get like -0.9. Or better yet, -0.99999, which is almost -1.
Mm-hmm.
Whereas here, we get -1.1 or -1.00001, because remember, that's way too close. This number is way too close to -3. So you have to give it a lot of decimals. -3.0000, so many zeros and then 1. The point being, the numerator is almost -1. The denominator is 0, but what's the difference? 0 from the right and 0 from the left have two different signs, and it has an effect in the result here. Does that make sense?
Yes, Professor.
That's why you, excellent. That's why you have to figure this out. In this case, negative over positive is negative. In this case, negative over negative is positive. And this is negative infinity. This is positive infinity.
All right,
Excellent.
perfect. Thank you.
My pleasure. All right, let's look at this example. If you plug in and you work it out, class, you can always plug in. You get 0 over 0. It's an indeterminate form, and indeterminate form means really more work. What do we mean by more work? Use your algebraic techniques. Now, we need to factor the numerator and the denominator. Before we do that, because x is approaching 4, most likely the denominator has a factor of x minus 4 that creates the 0 in the denominator. So you really should have an idea how to factor this. Of course, it's a simple factoring, but even if it's not, remember that. So the top is x times x minus 4. The bottom, you want two numbers is -4. The sum is -3, so -4 and +1. But again, because x approaching 4, you should have known that there should be a factor of x minus 4. This should help you factor easily. We get rid of the common factor. And now if we plug in 4, this becomes 4, this becomes 5. We are done. If you plug in 0, you get 1 minus 1 over 0, or you get 0 over 0. I hope you recognize that you get 0 over 0 again. And we discussed it already that if you have a square root, the technique is the conjugate, meaning you multiply by the conjugate of the numerator. So you multiply by the same thing and you change this to a plus sign. And at the same time, you divide by it. The reason you do that, because this expression is equal to 1, and that's okay. Bear in mind, h is approaching 0. This is the problem. The 0 in the denominator is a problem. You're hoping to get rid of it. You never, ever distribute. You keep the denominator as a product. You don't distribute. You simplify the numerator, which means this piece squared minus that piece squared. In other words, this gives you the following. And so square root of 1 plus h comes out. And then minus 1. By the way, and nobody is going to mix up these two. This is 1. This is -1. Order of operations. So these two cancel each other. The h cancel out. And that's the idea. You're really hoping to get rid of that. And now if you plug in the 0, the denominator is 1 plus 1, 2. So the answer is 1/2. And before we move on, I really can't emphasize this enough. When you are working on a case like this, first you plug in. If it works, so be it. If not, then you move on with your techniques. Okay, in this case, it's the conjugate. But if it works out, so be it. Now, this is an example that, again, I have to plug in to see what I get. So if I plug in 6 here, I hope you recognize this is 0. So this is 3. So the numerator is 3. You square this one, you get 36. Minus 7 times 6 is 42 and 12. So you didn't get 0 over 0. So if you start multiplying by conjugate and dividing by it, you're wrong. So the numerator is 3, the bottom 36 minus 42 plus 12 is 36 minus 30 or 6, which makes it 1/2. The limit of 1/3 minus 1 over x as x over x minus 3 as x approaches 3. This is a complex fraction, everybody. And if you plug in 3, you get 0 over 0. So the technique is LCD, the least common denominator. You notice the numerator has 2 fractions. The denominator doesn't have any. The LCD is 3x. You multiply and divide by 3x. When you multiply these two, this one times this one gives you x, this one times this one gives you -3. The product of the denominator, you don't touch anything. You keep it as a product. Why? Since x is approaching 3, x minus 3 creates a 0. 0 in the denominator is not good. You're hoping to get rid of it. And we do. Plug in 1 over 9 is the final answer. We want to evaluate the following limits if they exist. Here's the graph. The limit of f of x plus 5g of x as x approaches -2. Reminding everybody of the one-sided limit. A function has a limit at a if one-sided limits are identical. That's the meaning of that. So with that being the case, how do we approach this? We start with the limit laws. The limit of this piece plus 5 times the limit of this piece as x approaches -2. So we look at each case. The red function is f of x. X is approaching -2. So here's number -2. If you come from the left, you're going this way along the curve. From the right of -2, you're going this way, and the answer to this one is the y coordinate of this point, which is 1. For g of x, the blue function, -2 from the left and right, takes us from the left, and from the right takes us to this point, and this point, as a y coordinate -1. So you say this is 1 plus 5 times -1, and it's -4. And you're done with the first part. You need to understand the limits. Just for the sake of argument. This is -1, even g of -2 is -1, there is no discontinuity. But f of -2 is the y coordinate of the solid point 2. Don't mix them up. The limit of f of x times g of x as x approaches 1. We separate them into two limits. The limit of a product is the product of the limits, and we look at each case. X is approaching 1. So from the left side, we are here. From the right side, also, we are here. And as far as the f function is concerned, we are moving towards this point, and this point has a y coordinate. But the limit of g of x as x approaches 1 does not exist. And let's see why. If we are coming from the left, we are moving this way. And we are going towards this point, and this point has a y coordinate -2. However, if we go towards the right side, we are in this branch. And this one has a y coordinate which is different, -1. So the limit of g of x as x approaches 1 doesn't exist. Therefore, the limit of the product of f of x and g of x doesn't exist as x approaches 1. And you're done. But I want to quickly show you a second method. And this is fine. This is perfect. Okay. The second method is to do the following. Finding this limit as x approaches 1 from the left, and then as 1 approaches 1 from the right. So from the left, this one is 2 no matter what. This one is -2. The product of these two is the answer, -4. But from the right, the limit of f of x times g of x as x approaches 1 from the right. This is 2 from both sides, doesn't matter. So 2 times the limit of g of x as x approaches 1 from the right is -1. And the two numbers are different. The limit does not exist. So here's method 1. Here's method 2, proving the limit of f of x times g of x as x approaches 1 does not exist. Now, a couple of items of interest. One of them was f of minus 2 that I explained. The functional value is a solid point having y coordinate equals to 2. So that's the answer. For g of 1, again, you look for a solid point, you find a solid point here. What is the y coordinate of this solid point? -2. So we want to distinguish between the functional value versus the concept of a limit. Don't mix them up. What is the limit of f of x over g of x as x approaches 2? Well, doesn't exist. Why is that? Because here's number 2, everybody. And f of x is the red one. So from the left and right, let me just so this is number 2, and from the left, let me just erase everything. From the left, okay, and the right, we are moving towards the same. Some number, whatever you read, maybe you read 1.5, 1.4, but the point is this does exist. But for the g of x, the blue function, as we approach to from the left and right, the answer is the same, 0. Since the denominator is 0, the denominator approaches 0, while the numerator approaches a non-zero number, a number over 0. In this case, we say it's undefined, okay? If g of x is between 2x and x to the power 4 minus x squared plus 2, for all x, we want to evaluate the limit of g of x as x approaches 1. So we are looking at what's called the squeeze theorem, also known as the sandwich theorem, because g of x is sandwiched between the two functions. So when g of x is in between, and the limit of f of x as well as the limit of h of x, both of them as x approaches a are the same, the one in between results in the same limit. So with that being the case, let's take a limit of 2x as x approaches what number? 1. So it's just plug in, you get 2. Let's take the limit of the right function, x to the power 4 minus x squared plus 2, as x approaches the same number, 1. So if you plug in, you get 1 to the power of 4 minus 1 squared plus 2, and you get 2. Because these two are identical, then the one in between, the function in between, the limit of g of x as x approaches 1 is equal to 2, and you have to mention y by this squeeze theorem. By the squeeze theorem. Part B, prove that the limit of square root of x times the brackets plus 1 plus sine squared 2 pi over x close bracket as x approaches 0 from the right is 0. So the technique is as follows. You want to pay attention to that when you want to prove something like this. So what do we do? Just in case, everybody can hear me, right, class?
Yes, Professor.
Yes.
Excellent, thank you, because for a second I thought something happened to my head. The technique is, we know sine is always between -1 and 1, regardless of its argument. Alpha is the argument of sine. So if sine alpha is between these two numbers, then sine of this argument 2 pi over x is also between -1 and 1. We want to bring this up. Remember what we are going to do. So we need to square this. If I want to square this, I get sine squared. If I square this, I get 1. But it is important to know the left side. When you square it, the left side becomes 0. Here's the idea. Not that the left -1 squared becomes 0. Is that sine is between -1 and 1. So when you square it, worst case scenario becomes 0. Okay? So if you have any negative number, -10, and you square them from a negative number to a positive number, the negative side, remember you're squaring it, it cannot be negative, so it becomes 0. That's the idea. And the next step is, so we got this one. The next step too is to create 1. So add 1 to every side of this inequality. So this becomes 1. This becomes what we want as a bracket, and this becomes 2. So we got the bracket. The next step is to multiply by square root of x. And remember what happens with the multiplication. If you have inequality and you multiply by a negative number, it flips over. However, because square root of x and x is approaching 0 from right is positive always, then the sign does not switch. So let's multiply this one by square root of x, this one by square root of x, and this one by square root of x. So what we have in between is the expression we were looking for. We also are interested in finding the limit as x approaches 0 from the right. Therefore, we're going to take the limit of the left side as x approaches 0 from the right, as well as the right side. And as you know, this gives us 0. The limit of square root of x as x approaches 0 from the right is 0. Also, the limit of 2 times square root of x as x approaches 0 from the right is 0. If this gives us 0 and this gives us 0 when we take a limit, according to the squeeze theorem, the one in the middle, when we take a limit, gives us 0 by the squeeze theorem also. So if you happen to have sinusoidal function, sine, cosine, the technique is to start with this. Find the limit of 2x plus 12 over absolute value of x plus 6 as x approaches -6. And anytime you have an absolute value, you have to go with one-sided limit. And so we are going to look at this from the left side of -6. And to do so, I'm reminding you of the one-sided limit theorem that says the limit only exists if both sides result in the same thing, right? The second thing I want to remind you is the absolute value. Recall, absolute value of x is x if x is greater than or equal to 0, and negative x if x is less than 0. Therefore, absolute value of x plus 6, drop the absolute value if x plus 6 is positive That means x is greater than or equal to -6. I should say non-negative, okay, instead of positive. And it becomes the opposite of that if x is less than -6. So from here, we can see this one. And so with that being the case, what happens here, because we are approaching -6 from the left, we are going to replace the bottom with this. And the top, you can factor the 2 out. So we have 2 over -1, and the answer is -2. The limit of -2 is -2, regardless of x approaching what number. We are going to look at the same thing, but this time as x approaches -6 from the right. In which case, again, we factor out the 2 from the numerator, but the denominator, according to this, you just drop the absolute value because you're approaching -6 from the right. We drop the x plus 6. And becomes 2. The limit of 2 as x approaches -6 from the right is 2. Are these two identical? The answer is no. Therefore, the limit does not exist. So the reason why, because one-sided limits are different. A second method would be to simplify this expression first using this. So that expression, and I hope you realize this, 2x plus 12 over absolute value of x plus 6 becomes 2 if x is greater than or equal to -6, and it becomes -2 if x is less than or equal to -6. And now you take a limit of, instead of taking a limit of this, you take a limit of this as x approaches -6 from the right, becomes 2, from the left becomes this, and we get to the same answer, meaning the limit does not exist.